Sara, escribe a la gente del departamento que empieza esto. Que luego van a venir todos tarde y...
Pues buenas tardes a todo el mundo. Estamos aquí para asistir a la presentación y defensa de la tesis doctoral de Daniel Pérez Grande.
Espera, el micrófono creo. Tienes que apretar.
Buenas tardes a todos. Estamos aquí para asistir a la lectura y defensa de la tesis doctoral de Daniel Pérez Grande. Antes de proceder a la presentación, el secretario de esta comisión va a leer la normativa vigente.
Hola, buenas tardes. Según el artículo 14.4 del Real Decreto 99/2011, la tesis doctoral se evaluará en acto de defensa que tendrá lugar en sesión pública y consistirá en la exposición y defensa por parte del doctorando del trabajo de investigación elaborado ante los miembros del tribunal. Los doctores presentes en acto público podrán formular cuestiones en el momento y forma que señale el presidente del tribunal. Según el artículo 14.7, el tribunal emitirá un informe y la calificación global concedida a la tesis de acuerdo con la siguiente escala: no apto, aprobado, notable y sobresaliente. El tribunal podrá proponer la mención de cum laude si la calificación global es de sobresaliente y se emite en tal sentido el voto secreto positivo por unanimidad. La universidad habilitará los mecanismos precisos para la materialización de la concesión final de dicha mención, garantizando que el escrutinio de los votos para dicha concesión se realice en sesión diferente de la correspondiente a la defensa de la tesis doctoral. Muy bien, pues con eso es todo. I think we wanted to switch to English from this point on.
Okay. All right, so if we can start, welcome everybody. Thank you for coming. Thank you to the tribunal for being here, and also to my thesis director and to my thesis tutor. Okay, so the topic of my dissertation is fluid modeling and simulation of the electron population in Hall effect thrusters with complex magnetic topologies. That's a bit of a mouthful, but it's what we're going to talk about today. Since the presentation has quite a bit of equations, I wanted to start with something different. In particular, something that has been inspiring for me over the last few years. It's a famous phrase by Carl Sagan. I'll read just a little part of it. It says, "The surface of the Earth is the shore of the cosmic ocean. On this shore, we've learned most of what we know, and recently we've waded a little way out, maybe ankle deep, and the water seems inviting." So this phrase, as I said before, has been inspiring to me. I think it's because I really like the analogy between the cosmos and the ocean that Carl Sagan does, perhaps because I'm attracted to both. But it also begs the question of where are we now? This phrase was, was coined 40 years ago. Carl Sagan mentioned that we were ankle deep, so the question is, where are we now? I think charts like this give a kind of a good answer of, let's say, the reach of humanity into space. This shows all the scientific and exploration missions in the solar system. It's missing a few that I really like, the ones that are headed for interstellar space. And it also doesn't show the commercial space missions, the one that orbit the Earth and provide us with GPS, Earth observation, weather satellites, etc. But it is, I think, a good way to have a one glance at the presence of humanity in the solar system, even if it doesn't really answer the question of that I mentioned before. So even if ourselves if we haven't really gone out into the solar system that much ourselves, we've definitely thrown out our little submarine toys into this cosmic ocean, and they've been exploring the waters for us for quite a bit. We've thrown about 8,000 of these out there, and there's many technologies that are being researched today that are oriented towards expanding the reaches of humanity's presence in space. So today we're going to talk about one of these technologies. It's a rocket technology. In particular, it's called electric propulsion, and that's what I'm going to speak about today. So this the outline of my presentation. I'm going to start talking about space propulsion in general. Then I'll switch to Hall effect thrusters, which have been the topic of my study. I'll talk about characterization of electric propulsion thrusters in general. Then I will introduce the hyphen environment, which is the code that we've been developing over the last 4 years. I will talk about my main contribution to that code, which has been the 2D anisotropic fluid model for the electron population. I'll talk about the numerical meshing that we've done for that particular segment of the code. I will detail some of the tests that we've run on our side of the simulation, and then I will show some simulation results for an SPT-100, which is a type of Hall effect thruster that kind of demonstrate that our simulations are working as we want them to work at it. And then I will introduce some conclusions and future work. Okay. So if we're going to start talking about space propulsion, it's good to start with the rocket equation. It's derived from Newton's second law. So sum of forces over a system is equal to the change in the rate of change of linear momentum. If we assume that the external sum of forces is 0 and we integrate state equation for between 2 time steps, for a system that's similar to the one shown here, which is a little kind of crude rocket. We can see that excuse me, sorry. This is really bad. If we see the little rocket that we saw here, it's ejecting mass at a certain exhaust velocity, and that mass ejection increases the velocity of the rocket by a certain delta V. And the equation that relates all of those terms is this one over here. Again, we see the exhaust velocity, and we also see the mass ratio that is employed to obtain that certain change in velocity. So this equation was derived by Tsiolkovsky in 1903. He's being quoted as being one of the fathers of rocketry, hence the very cool glasses. And the equation itself is very interesting because we can turn it around and we can see that the total mass fraction for a certain increase in velocity is inversely proportional and also exponentially proportional to the exhaust velocity of the jet, which means that as small increments in this number here will give us good changes or rather large changes in the mass fraction that's required for a certain mission. Of course, the delta V is what we use to determine a mission in space. This is a bit of a subway map of the solar system, and every stop or let's say every 2 stops here is separated by a certain change in velocity that's required. So, for example, to leave the surface of the Earth and go into low Earth orbit, we need a change in velocity of about 10 kilometers per second. We'll introduce now a couple of terms that are more related to traditional, let's say, terms related to rockets. One is the ISP, which, as you can see, is proportional to the exhaust velocity. And the other one is simply the thrust equation. These, let's say, 3 magnitudes pretty much characterize every type of rocket that we have. Of course, the quantities that characterize the mission itself is the delta V and the total mass fraction that's required to achieve a certain mission. As we can see here, the exhaust velocity, or the ISP, is a really attractive value because increasing the ISP, or the exhaust velocity, will greatly reduce the amount of mass that we need to get from one place to another. So the question then becomes, how do we increase that ISP? How do we make or jet have a larger exhaust velocity? And this leads us to the classification of rockets, the traditional classification of rockets, and it's related to the origin of the energy that is being converted into kinetic energy in the rockets. So we have chemical, electric, and nuclear energy. Let's say as a source. But we can also do a secondary classification between thermal and non-thermal electric. So thermal rockets are those in which some sort of energy is converted into thermal energy of the mass that we're ejecting, the propellant, and then said energy is converted into kinetic energy in the jet. Non-thermal electric rockets, which are the ones that we're going to focus on today, actually operate a little bit different, and we'll talk about the mechanisms in a moment. The major difference between these 2 types of systems, in particular for non-thermal electric and perhaps chemical propulsion, which are the most representative types of rockets, of thermal rockets, is related to the type of thrust and specific impulse that we achieve with the rocket. So for non-thermal electric, we have low thrust and high specific impulse versus high thrust and low specific impulse for chemical rockets. This leads to this cascades onto a series of characteristics for the system. One is related to the duration of the propulsive maneuvers, the type of transfer trajectories, whether they're low-energy Hoffman trajectories or spiral trajectories, whether they're operable or not within the atmosphere, and what they're limited by. So electric propulsion rockets are limited by the state-of-the-art electrical propulsion systems, which is related to their reliability and their robustness, whereas chemical rockets are typically limited by the energy stored in the chemical bonds and the mass flow that that a rocket is able to produce. Of course, again, what we're focusing on is those that are able to deliver high specific impulse because of the gains that we mentioned before. Okay, so let's talk a little bit about non-thermal electric propulsion. There's many types of devices that that fall in within this classification. You can see here that they show quite different, let's say, performances in terms of specific impulse, thrust, and efficiencies. By the way, these let's say these performances are not cannot take arbitrary values. They're constrained by the efficiency equation here. But as you can see, there's many different types. The ones that we're going to focus is on Hall effect thrusters, and I'll mention now why they're let's say of interest to us. Okay, so Hall effect thrusters were introduced in the 1960s, developed initially in Russia, and first deployed in 1970. Today they're used for attitude control and orbit positioning in small to medium-sized spacecraft in all kinds of missions, exploration, scientific, and commercial. They're the main technological competitor to the ion engine, which some of you might be more familiar with. In terms of figures of merit, they go at a, let's say, moderate ISP between 1300 and 3000 seconds of ISP, and they've been recently tested to 5.4 newtons of thrust in NASA's X3 thruster, which runs at about 100 kilowatts. Typically, they've had some operational life limitations at about 10,000 hours. This is due to erosion due to ion bombardment of both the thrusters and different components in the subsystem. But some developments, which we'll mention in a second, have been able to double these limitations. And finally, there's many different types of Hall thrusters. Although the basic physical mechanisms on which they rely on are all very similar. So let's talk a little bit about those basic physical mechanisms. I'm going to use an annular type Hall thruster. Not every Hall thruster is annular, but I think this fits our explanation nicely. So let's assume that we have an electric field which is in the axial direction and a magnetic field which is in the radial direction. So under a combination of an electric and magnetic field in this way, charged particles experience what's known as an E cross B drift, which is a result of the Lorentz force being applied over the charged particles. And what happens is that the particles tend to have a drift that is both perpendicular to the electric field and to the magnetic field. This drift itself is characterized by a quantity that we know as the Larmor radius, which is related to the intensity of the magnetic field and the mass of the particle. So it turns out that for representative intensities in our devices, electrons have a Larmor radius that is much smaller than the characteristic size of the device. But this is not so for ions, which have a Larmor radius that is much larger. Therefore, we say that electrons are magnetized, they're confined by the by the magnetic field, and they follow a close electron drift in the azimuthal direction. This drift is actually called the Hall current, and it's the one that gives name to the device. And the ion population is unmagnetized. Now, the electrons in their azimuthal drift will encounter neutral species or neutral atoms. They can collide with them and produce two different types of reactions. One is an ionization reaction. They convert the neutral atom into an ion, which is actually the one that is then accelerated by the electric field to produce thrust. And they also have another collision which allows the electron to move in the direction opposite to the electric field. And this is what's known as classical transport, although a large part of the cross-field transport in the electrons is due to non-classical effects, of which we'll talk about in a second. Finally, both the electrons and the ions, so the complete plasma, interacts with the walls of the device through what's known as plasma sheaths, which represent the boundary layers in the plasma. Okay, so let's continue just a second with operational principles. First of all, the magnetic field is produced by electromagnetic coils or permanent magnets. We have the neutral atoms of which I spoke before are introduced into the back of the channel of the device, let's say through an injector. We then have a hollow cathode, which is an external electron emitter, which is the one that provides the electron current necessary to begin the ionization and begin the discharge in the plasma. This device also will provide what we call the neutralization current, which is the one that ensures that the exiting current in the thruster is current-free, and that therefore we are not electrically charging the device and the spacecraft. There's a PPU, a power production unit, which is connected to both the hollow cathode and a back region, and a region near the injection point, which is the anode, and establishes a voltage differential between those two. That's actually responsible for the electric field that the plasma is experiencing. And finally, what happens is that the plasma itself is responsible for locally selecting the value of the electric potential due to the conductivity and local characteristics of magnetic confinement. And it can be demonstrated that the plasma itself is the one that closes the circuit between opened by the PPU. Okay, so let's talk about how we characterize electric propulsion thrusters. So I'm going to speak very briefly about the issues with characterization of thrusters. As I've shown before, there's a few physical mechanisms, pretty basic, but it turns out that the interaction between these basic physical mechanisms already leads to a complex response which is difficult to analyze. Furthermore, there's non-classical mechanisms which we have not characterized very well that also have an effect over the response of the thruster. Let's say the design space of a Hall thruster, or this could be a EP thruster or electric propulsion thruster, sorry. In general, it's something like this. There is a relation between thruster design, thruster performance, and the plasma physics, and the interaction between these three is not fully understood, which is the reason that when we look at, for example, a graph of showing low-power Hall thrusters, the ones that fall between 100 and 400 watts, the efficiency that they present is all over the place. It's a cloud of points instead of a single nice line. And the reason is that we have not characterized that design space well, and it also turns out that this leaves with a lot of optimization opportunities that can still be explored. This is the reason why magnetic fields have been evolving over the year, or the magnetic field design in the thrusters has been evolving over the years. The last trend is magnetic shielding, which was actually discovered by chance in this thruster over here. It's the BPT 4000, which eroded to a moment in which the magnetic field resembled something like this, and then almost stopped eroding completely. So all these optimization and characterization opportunities still exist. So since we don't know exactly what happens in these thrusters, how do we characterize them? Well, the typical way has been experimental studies. This requires construction of both the device and whatever platform you're using to test the thrusters. So it's either a vacuum chamber here on Earth or a technology demonstrator satellite. Obviously, you have to apply plasma diagnostics, which is a field on itself in order to achieve some characterization of the thrusters. And typically, they're constrained by budget and time. But we have another option, numerical studies. So recently, maybe not that recently, over the last 20 years or so, thanks to increasing computational power and it becoming more affordable, we now have what we call virtual laboratories. So virtual laboratories allow us to explore the design space that we spoke of and make predictions in a way that simply experimental studies cannot. However, the fidelity of the results of these virtual laboratories tends to be questioned because it's always related to the type of models and the physics that you're actually simulating. And an initial good classification between the type of numerical studies is whether they focus on the plasma discharge itself or the plume region, and that's because they operate on physical regimes that are very different. For this thesis, we focus on the plasma discharge region. Okay, so in terms of simulation models, what approaches do we have? So we have first, I'm going to speak about two approaches here. We have a particle approach. If you consider the cloud of plasma, which is a large number of elementary particles that is not computationally approachable. So what we do is we clump these particles together in what we call macro particles, and that makes the problem approachable computationally. And if we know the position and velocity of each of those particles at any given time, we're able to characterize the plasma. Of course, these macro particles follow the electric and magnetic forces that are in the environment in which they operate. So there's some pros. So we don't make any assumptions on the distribution shape, or maybe little assumptions, few assumptions on the distribution shape or the collisional processes, what we call a kinetic model. You can derive macroscopic quantities from them. And in theory, it's considered a parameter-free approach. There are some cons, though. Because we're using a number of macroparticles that is reduced from the total number of elementary particles in the gas, there's a lot of statistical variance or numerical noise. There needs to be a modeling of direct and indirect particle interactions, which will have a toll on computationally. And also the computational load depends on the dimensionality of the problem, the subset of Maxwell's equations that you solve, and typically the dynamics of the fastest species, which normally are the electrons. And it's normally considered a bit of a brute force approach due to the scales that need to be resolved. Another option is to model the plasma as a fluid. What we're trying to obtain here is an idea of how an analytical six-dimensional function, which depends on space and velocity, evolves over time. Boltzmann gave us the famous equation which relates the evolution in time of this distribution function, in which typically we have problems to, let's say, analyze the impact of collisions over the distribution function. Now, you can derive transport equations from this equation over here for each of the variables that you're interested in. So, for example, plasma density, particle flux, energy flux. But these transport equations are an infinite series because every equation depends on moments that are resolved by the next equation, which means that normally we need to truncate those equations in a way. A typical approximation to that is to assume a certain shape of the distribution function. This is the known Maxwellian shape of the distribution function, which depends on a certain temperature and the average velocity of the particles. We also need closures for these collisional terms over here, which we don't know exactly how to model. And in terms of pros, well, the computational load is reduced greatly in comparison to the particle approach because the scales are now associated only to numerical stability. In terms of cons, there's obviously a larger number of free parameters. You cannot reproduce kinetic effects, those effects that are related to the shape of the velocity distribution function, since we typically have to assume a certain shape in order to close off the equations. And they're typically not appropriate for outlier species, the ones that are rare, let's say, in the plasma, like secondary ions or secondary electrons. Sorry, doubly charged ions or secondary electrons. Okay, so having said all of that, let's introduce the work that we've done. So we've been developing over the last few years a code. It's called Heightened. It stands for Hybrid Plasma Thruster Holistic Simulation Environment. It's a hybrid code, as the name mentions. The name hybrid is due to the fact that we model the electron population as a fluid and the heavy species, so neutrals and ions, as particles. Excuse me. As particles, which gives us a compromise on the computational load, but allows us to retain some kinetic effects in the distribution of the heavy species. This approach is also a legacy from other codes that have been developed on NAP2 that are well known or that have been worked on, and it allows us to recover some performances and also some high-level physical effects in the plasma. And it's actually the type of approach of choice for Hall effect thrusters. So we can see here some papers that have been, or some codes that have also used this approach to solve the problem that we're looking into. So now that we've done this pretty massive introduction, we can talk about the scope of the thesis. The idea is that if we are able to make progress with numerical simulation codes for a wide range of electric propulsion, then we will be able to reduce development costs and time, and also reveal optimization opportunities for future thrusters. So Heightened is the first full 2D RC axisymmetric hybrid code that we know of. The plasma regime that we've targeted is one related to weakly collisional species, strongly magnetized electrons, and negligible self-field production, which means that the MHD regime is in principle out of scope. We focus very much on being able to simulate the effects of complex magnetic topologies and larger simulation domains compared to other codes. And this is thanks to the electron fluid approach that we followed within obviously the model's limitation. And this is our main contribution to the work that we've done. And at the moment, it's been tested for stationary plasma thrusters, which is a type of Hall thrusters. We believe that it's expandable easily to other types of Hall thruster configurations, and we're focusing our work at the moment on applying it to thrusters that depend on magnetic nozzles. In terms of philosophy of design, we've focused on versatility, test-driven design, and modularity, which is something common, I think, in the developing world, in the code developing world. And we've also focused on user and developer friendliness, which has implied that we needed to provide adequate documentation for the code. We've also used industry-level standards and very widely known libraries such as HDF5, OpenMP, and so on. Okay, so in terms of the code itself, it has 3 program units. One is the Heightened set. This is where we set all of the parameters in the simulation, the meshes, everything that you need to actually start the simulation. This provides us with two files that go into what we call the heightened core, which is a compiled block written in Fortran 95 language, which is actually responsible for advancing the simulation. And this provides us with another two files. One is related to all the data that we want to obtain from the simulation, and the other one is provided with the exiting state of the simulation. And that's analyzed by the hyphen post unit, which is the one that we use to obtain diagrams, plots, and so on. As I mentioned before, we focused on the electron fluid module, which is about half of the core, and we've also incorporated a number of utilities for the hyphen set. Okay, so the hyphen core, which I think is the more interesting one that we want to talk about today, is organized like this in terms of algorithmic flow. It has, as I mentioned, two big modules. One is the particle and cell module for the heavy species, and the other one is the fluid module for the electrons. The heavy species module is responsible for advancing the discrete particle populations, and also for weighting them, which is the way that we obtain macroscopic quantities such as density, ion currents, and so on. And it uses, in order to do this, the electron temperature and the electric potential in the plasma as an input, and also some quantities that are related to what happens in the boundaries. On the other side, we have the fluid module, which is the one responsible for advancing precisely the electron temperature and the plasma potential, and uses as an input the weighted quantities from the particle and cell code. As you can see here, the main time step in the simulation is given by the particle in cell module. The electron fluid module actually uses an intermediate number of steps due to stability concerns for the equations that we model. And also, as you can see, between the two sides of the codes, there's some interpolation steps. The reason behind that is that they use different meshes, and we'll talk in a moment about why that is. Okay, so as I said before, particle and cell module, which was developed in its entirety by my colleague Adrián Domínguez, is responsible for advancing the particle side of the simulation and obtaining weighted quantities related to the heavy species. It uses a mesh in this, which looks maybe like this. It's a structured mesh, which is easy we use because it's easier to identify particles within structured meshes, but also to do this weighting procedure to obtain the macroscopic quantities on these sort of meshes. The fluid module, on the other hand, is pretty much only does two things. It integrates the energy equation, which gives you the rate of change of electron temperature, and then it solves the generalized Ohm's law and the current continuity equation to obtain the electric potential and the electron currents. As I mentioned before, it uses as an input the weighted quantities from the particle and cell side, and it uses a dedicated mesh that looks something like this, and I'll speak in a moment about why the mesh looks like this. Okay, so let's talk about the fluid model that we've incorporated into the fluid segment. It's based on the 16-moment approximation by Barakat and Shunk, and it also uses Bittencourt's model for the collisional, mainly for the collisional models. It's a full 2D model, which means that we don't make any assumptions on the thermalization of magnetic field lines, which allows us to recover larger simulation domains and these complex magnetic topologies that we've been speaking from the beginning. It uses a two-temperature approach to the velocity distribution function. It is related to experimental evidence for anisotropicity in Hall effect thrusters, but it also allows us to recover bulk effects that are related to non-uniform magnetic fields, such as the magnetic mirror. So for example, here we can see a distinction between a velocity distribution function that is Maxwellian and what we call bi-Maxwellian, in which we have two temperatures that are used to define it. By the way, these two temperatures are related to the, let's say, the preferent directions set in the problem due to the magnetic field. So the parallel direction refers to the parallel direction given by the magnetic field, whereas the perpendicular direction actually refers to a whole plane, which in the cylindrical coordinates is made up of the azimuthal direction and a perpendicular direction which is kept in the RC plane. And this is important to remember for, let's say, the rest of the presentation. Okay, so I'm just going to show the equations very quickly here. Nobody gets scared. Okay, I'm just going to pass over them very quickly because I'm more interested in the assumptions that we've used to resolve them. And also, this is just to show that we kind of stop at or truncate our model at the perpendicular heat flow equation. And this gives us the 12-moment approximation which we spoke of. So in terms of assumptions, axisymmetricity is one of the assumptions that we've based the code on. We've also neglected the viscosity term, which means that the pressure tensor is diagonal. We've assumed a null Debye length limit, which means that there is no region within the simulation that cannot withhold quasi-neutrality. That means that the sum of partial ion species always has to be equal to the plasma density. And this also confines the, let's say, the boundary layers, which are actually a non-quasi-neutral region, to outside of the simulation domain. In terms of closure, we used, Barakat and Shunk actually used an approximate expression for the velocity distribution function. They introduced a perturbation term which allowed them to close off the fourth and third order tensors as a function of lower order tensors. We used the ideal gas law. And we've done some dimensional analysis which allowed us to, let's say, reduce the complexity of the equations. The first one was the comparison between the drift kinetic energy of the electrons and the thermal energy. And it showed, well, we assume that the electrons have a dominating thermal energy. And a second dimensional analysis relates the terms related to, let's say, the heat flow equation to these terms over here. The conclusion that we obtain from here is that convective and non-stationary terms in both the momentum and the heat flow equations can be discarded, and they become state equations, as we'll see in a second. We've used some sources and sinks related to, let's say, the amount of plasma that is being generated and the energy that is being used to generate said plasma. We use these collisional frequency terms, which are related to cross sections, and the thesis itself has quite a large section devoted to that, although we're not going to go into that in this presentation. We use Maxwell-type molecule interactions for all the collisional terms, both in the momentum and energy equations, and we use Crookes' relaxation model to close off the heat flow equation. Okay, so that being said, as I mentioned before, the electron fluid module actually does two things. First of all, it solves the current continuity equation. The current continuity equation is obtained from the mass continuity equation and the quasi-neutrality condition. This allows us to model external current sources, such as the one that is represented by the hollow cathode, as a simple term, I sub d, on this equation over here, which will be either zero or non-zero in some regions of the simulation domain. It also solves the momentum equation, and again, nobody gets scared. I'm just using this to talk about a few of the terms here. First of all of the terms related to collisions and the magnetic confinement. The collisions in the equations are related to the total electron resistivity, which sums all of the collisional frequencies that are between the electrons and the heavy species. And then we have the beta here, which is the Hall parameter, which is the one that defines the magnetic confinement in the simulation, okay, or in the equations. Now, as you can see here, the parallel direction and the perpendicular direction are vastly different in terms of these factors here. One uses the beta while the other does not. And this is a result of the perpendicular direction being confined by the magnetic field, but the parallel direction being free in terms of the magnetic field confinement. This beta here, by the way, can be of between 10 and 100, depending on the region that we're exploring. So the factor here is the two factors here are pretty different. Now, if you've been following me closely, I said before that we're using an axisymmetric assumption, but we still retain the terms related to azimuthal gradients here. Why is that? Well, it turns out that we know from experimenting with Hall thrusters that the cross-field transport of electrons is actually much larger than the one that would be given by solely classical terms, which are the ones that I'm pointing out here, which means that we need to retain this forcing term that normally originates in the azimuthal direction. So we use a forcing law for it, which takes this form. That comes from, let's say, legacy codes or the way that it's been modeled generally. But the most important thing of this law is that we use what we call an effective total electron resistivity and an effective total Hall parameter. This effective resistivity and Hall parameter are related to the effective electron collisional frequency, in which we add to the total electron collisional frequency two additional collision frequencies, the anomalous collisional frequency and a near wall conductivity collisional frequency, which are related to some effects that we are not sure how to model. This anomalous collisional frequency, which is one of the main parameters in the code, is related to the is proportional, to the gyro frequency through a, well, this is just putting that formula in there, and this anomalous collisional frequency is just simply proportional to the gyro frequency. So it turns out that the reason why we do this is because there's non-classical short-circuiting of the electron cross-field transport, which can be due to a number of reasons, either E cross B or diamagnetic drifts in the azimuthal direction, turbulence, waves in the plasma, roughness in the device's walls, or even scattering of different electron populations. So since there's a lot of people that have been working on this, but we are not 100% sure how these effects come into play, so we simply model it as a single free parameter in the code, which is this through this factor here, which is known as alpha anomalous. Okay, so as I said before, the continuity equation and the generalized Ohm's law come together to give us a system of equations in which we resolve the electric potential. Obviously, these are the electric potential gradients, which I've put here explicitly because since we use a mesh, that does not evolve in time, these gradient reconstruction coefficients are actually simply geometrical coefficients. There's other terms in this equation, obviously some drag terms due to heavy species. There's pressure gradients. There's the effects of magnetic non-uniformity. And obviously, since we're resolving the current continuity equation, the ion currents and the external currents. We also solve the total and parallel energy equations, which are actually the ones that give us the evolution in time of the electron fluid. You can see here that we use 2 time subscripts. The reason behind this is that we're using a semi-implicit method to solve these equations, in which some terms are, let's say, solved explicitly from the temporal scheme point of view, and other terms are solved implicitly, and this is because of stability concerns. Again, the terms that come into the equation are the advection terms, the gas expansion terms, heat flow terms, and some collisional and sources and sinks. I'm going to speak about this just a little bit closely because they come into play later. So forget about this big equation here. The only thing that you need to remember is that there is a term related to resistive or ohmic heating, which is what we remember from high school, Ri squared. And there's a second term related to an energy sink, which is the energy that the electrons are wasting, let's say, to produce ionization to start the plasma discharge, and also to excite some of the neutral atoms. And as I mentioned before, the heat flow equations also become state equations. They depend on pressure gradients and sort of drag term that comes from introducing the momentum equation into that one. We resolve the model using a cell-centered finite volume method, which is takes a conservative or integral approach in the strong formulation. It's recommended for non-structured meshes, and I'll mention in a moment why we need to use non-structured meshes. And it requires it requires a number of things. First of all, spatial discretization based on linear gradient reconstruction. We use the weighted least square method for that. It also requires the Gauss term the Gauss theorem and some integral approximation related to the flux of quantities at the faces of the mesh, and also of quantities within the mesh volume. So we are not in an initial condition problem. It's actually more of a boundary condition problem since we're solving the current continuity equation. That's just an example. So we need to look at the boundaries a little bit more closely. Obviously, in this type of axisymmetric domains, the domain axis is a very well-known boundary, but we also have ceramic or dielectric walls. That's just depending on the type of thruster. Not all thrusters have ceramic walls. We also have the anode boundary and some far field boundaries, which are the escape boundaries for the plasma. This is what we call a cathode boundary, which is simply the way that it used to be handled, or these escape boundaries used to be handled in other codes. And we also have these volumetric cathode elements, which are the elements in which we introduce the external intensity, the external current intensity. So the domain axis uses the typical approximation for axisymmetric, let's say, domains. That's not very interesting. The far field boundary is a little bit more interesting. We use non-homogeneous Newman conditions and also homogeneous Newman conditions in the boundary. So in terms of, for example, non-homogeneous Newman, this implies that the sum of currents of electrons and ions is equal to 0. And in terms of the energy equations, it implies that the total heat flow in those phases is equal to 0. More interestingly than maybe those are the material boundaries, or the physical wall boundaries. So as I mentioned before, there's a sheath or a boundary condition that affects the material walls in our simulation. So for a dielectric wall, and also for the anode wall, we'll get into that in a second, there's a region called the sheath region, which we've modeled as a stationary, collisionless, and non-quasi-neutral region. The reason why this region exists is because dielectric walls cannot hold electrical charge. Therefore, the sum of electric and ion currents must be equal to 0. And in order to do that, there needs to be this sheath over here that regulates the deposition of momentum and energy of both the electrons and ion species. So you can see here that we can obtain a model that also gives us this energy deposition and the very well-known sheath potential drop, which depends on all these quantities here. This is, for example, a solution from our sheath model. I can go into that later if you have more questions. But this is for a typical boron nitride wall, which is what typically Hall thrusters are made of. The anode condition is very similar to the previous one, with one exception. Instead of knowing the amount of current as a condition that's coming into the wall, what we now know is the potential at the conducting wall, which is a simulation parameter. It's set by the PPU, for example. And we also should know, for example, the potential at the other side of the sheath, the one that actually limits with the simulation domain. Now, this is actually part of the solution, and it comes into the equations through this equation over here. Remember that we're solving the continuity equation, which means that we have a condition for the electron current that's being allowed to pass by the anode boundary. Now, we cannot solve it in this way because this equation is actually nonlinear, and again, I mentioned that we need to have linear conditions, so we linearize this equation with regards to a certain guess sheath potential drop on which we iterate through a Newton-Raphson method, and this is what we call the iterative matching algorithm. Finally, we have the volumetric cathode elements, which actually represent the PPU, the type of PPU control that we have. They can either represent the constant voltage mode, in which we select a second electric potential referential or reference, within the simulation domain, or a constant current mode, in which we pick the discharge current that's being inputted by these in these elements. Okay, so I mentioned before that the meshes for our model are a bit distinct. The reason behind this is that we have something like this. If you remember, for example, for the momentum equation, the perpendicular and parallel directions showed widely different conductivity factors. And again, I just wanted to point out that the beta here takes a value between 10 and 100. So the difference between these factors is between 110,000 or even more, depending on where we are in the simulation domain. So when this happens, what happens is that if you use a numerical mesh like the one that's shown here that is not aligned with whatever is causing the anisotropicity in your system, in this case the magnetic field, then you start to have these terms here which are actually what we call cross-contamination terms, which pretty much mix the diffusion coefficients or the conductivity coefficients of the two directions. So that means that you'll have something that's called numerical diffusion. You'll have a greatly increased numerical diffusion across the magnetic field, and that is something that we wanted to avoid because, as we know, the electrons are highly magnetized and therefore confined. So in order to avoid this, we need to start by assuming that the magnetic field is what we call static, so it's solenoidal, stationary, and irrotational. And therefore, we can derive what we call magnetic coordinates. So the first one is the magnetic scalar potential. It comes from the irrotationality condition, but what's important is that gradients of this magnetic scalar potential, sigma, are always perpendicular or locally perpendicular to the magnetic field. The magnetic streamline function, which is derived like this, is always local. Gradients of the magnetic streamline function are always locally parallel to the magnetic field. So if we had a magnetic field like this, which is a representative magnetic field of a Hall thruster device, we have lambdas and sigmas that look like this. And we can use these surfaces, which, if you consider that this is actually an axisymmetric condition, so these surfaces are actually closed surfaces, this allows us to define these toroidal volume elements in which each of the faces is either closely aligned with the perpendicular or closely aligned with the parallel direction in the with regards to the magnetic field. And this allows us to pose the equations in a way in which we do not have numerical diffusion or in which we are greatly reducing the numerical diffusion. You can see here a mesh in the r-set direction, and you can see here a little element in which each of the faces is again either perpendicular or parallel to the magnetic field. So how do we do these meshes? Well, it turns out that we need the correct meshing, or in order to do these meshes, we need to find a good distribution of lambda and sigma. But what does good mean? Well, we have a number of challenges. First of all, as you can see here, lines that are separated, let's say these two lines, these two blue lines, these two lambda lines, are separated differently in this region than in this this region. That's because the separation, the actual separation between what we call isocontours, or lines of constant lambda or sigma, varies with the position within the simulation domain. Now, the domain boundaries also cut these lines in arbitrary precision. The domain boundaries are generally never constant lambda or sigma lines, which means that we need to cut these lines arbitrarily, and that leads us to using a non-structured mesh, as we mentioned before. And one of the things that we wanted to be able to simulate were singular points, and it turns out that singular points need to be handled also carefully and also require the use of a non-structured mesh. So we've implemented two approaches towards finding this good mesh. One is an inverse rate of change approach, which is the one that we presented, which basically you take all of the values of lambda and sigma within the simulation domain, you set them up, you look for a local regression of that, and then you pick values of lambda and sigma that are separated inversely to the rate of change of lambda and sigma. And this ensures that you will have more or less correct spacing. And I'll show you in a moment this type of mesh. And we also use the exponential stretching method, which is detailed in the thesis, which was proposed by Araki. So we've done some mesh trials. This is the inverse rate of change mesh, as I said before. It provides with more or less good spacing. And these are the Araki meshes. The mesh generator that we've developed also allows us to do some manual correction in the meshes, which is why we can maybe play a little bit with how good or bad the mesh is. Now, in order to see how, let's say, how this mesh behaves, first of all, we look at geometric quality. That's just something that is well known by anyone that's used a mesh generator. So we look at smoothness, skewness, and aspect ratios. And the idea is to try to achieve the better values, the better statistics on all of those values as possible. So the method would be to basically do some meshes, then run them through the script that gives us the geometric quality. And then once we have a mesh that we're okay with in terms of geometrical quantity, then we look at what happens in terms of gradient reconstruction. Now, gradient reconstruction in our code is done through the weighted least squares method, which basically is based on the Taylor expansion around any given point, really, and provides us with these coefficients here, which are geometrical coefficients by which we can derive derivatives up to any order. Now we do trials with analytical trial functions, such as, for example, a first order function here, quadratic functions, or sinusoidal functions, and then again we pick the best characteristics of the weighted least squares that give us, let's say, some gradient reconstruction that we're happy with, let's say. So it's a bit of a custom approach and not 100% quantitative. Okay, so that's just been, let's say, all of what we've done until to the moment of actually, let's say, starting to run some tests on the simulation. So I'm going to go very quickly over some of the tests that we've done simply on the fluid module. So we used a particle in cell, so a particle time step from a different simulation code, in particular the HALMA simulation code, and we applied our fluid module to that time step, or that let's say the weighted conditions that we obtained from that. We saw that the results that we obtained were very similar to the ones that were obtained from the previous code. We also did some terms in terms of the explicit or semi-implicit temporal scheme that we implemented for the energy equation. This is the residual here, which tells us the change in a certain rate as the iterations progresses. And as you can see here, if we only use an explicit method versus a semi-implicit method, the explicit method got stuck, let's say, on a certain value for the residual, versus the semi-implicit method that was actually able to go down to almost arbitrarily low values of the residual, which implies that we were working on a stationary condition or exit condition. We did some initial condition sensitivity analysis, and spoilers, they all came back with the same results independently of the initial conditions, because again, it's a boundary condition problem. We did some time step sensitivity analysis. This is just varying the dt that we've used for the simulations. And it turns out that basically what happens is that within the stability limit, the only thing that happened is that the number of iterations till convergence went down as we increased the delta t. We also looked at the different models that we implemented for the PPU control and the volumetric cathode. This is some results for the electron currents, which Normally people don't show in the literature, and perhaps this is the reason why, because they look pretty weird, but we can talk a little bit later about why they look like this, or why we believe that they look like this. But in any case, this compares a constant voltage condition and a constant current condition and a single element volumetric cathode and a distributed element volumetric cathode. And it turns out that the only changes that we saw, if you look here, for example, is the perpendicular, the axial electron current, and they're spot on, same results. The only differences were in the parallel electron currents and only locally between the elements that we used for the cathode. We also did a mesh size analysis, and this is perhaps the most controversial of our results. It turns out that the electric potential that we solved was pretty similar independently of the mesh, but not so the electron temperature. This is due to, we believe, to a number of reasons: varying quality of the gradient reconstruction and varying quality of the mesh itself. Also, interpolation between the particle side and the electron fluid side. And perhaps one of the reasons as well is that we were running this with what we'll see in a second, it was a simulation with no turbulence, with no anomalous collisionality. And that simulation is very, very sensitive to what happens in the plume. So that might also be the reason why we obtain these various results, but we can talk about them later if you want. So I think let's say the crown jewels of our work has been the results that we've been able to provide for the SPT-100. The SPT-100 is what we call or what people call an open source thruster. Pretty much everybody knows the magnetic field design, some of the geometric characteristics, and also the performances. So for example, this is, let's say, the design for the thruster. By the way, this is one of the utilities that we've been able to develop throughout the thesis, which allows us to play around with the magnetic circuit design. And this is the resulting magnetic field, which is very similar to, as you see here, for example, this is the magnetic field in the thruster center line, and this is very similar to what is known from experimental conditions. And we also have the performances of the thruster. They've been tested many times, and we've used as a reference the original performances by Brophy in '92, which was actually the first time that the Americans got their hands on on a Hall thruster. Okay, so I just wanted to go very quickly over some of the things that we're going to talk about in a second. So first of all, we've looked at power balances within the thruster. The original power balance is an electrical power balance. It equates the total work produced by the electric field to the discharge power in the simulation. And then you can also do a kind of like a partial balance, a partial power balance, where you input all of the different terms that are related to both the particle side and the fluid side. We can also look at thrust. It can either be derived from the momentum flux that is carried by the particles exiting the thruster, or due to the electrons, since the azimuthal current in the Hall thruster is actually the one that's responsible for coupling the thrust to the thruster's magnets. So by looking at this Lorentz force of the Hall current over the magnetic field, we can also obtain the thrust. We've looked at overall this equation overall performances, this equation we introduced at the beginning, and also partial performances like utilization, current, production, and divergence performance efficiency, And in terms of the simulation parameters that we've used for the simulations that I'm going to show today, well, we use a constant voltage PPU control at 300 volts. We introduced 5 milligrams per second of xenon flow, which is what is reported experimentally. And we use a single element cathode, which you'll see in a second in the simulations. These are just some characteristics of both the sheath model and the collisional models that we've used to run these simulations. Again, we can talk about them more in the questions round at the end. And in terms of the, let's say, some of the more numerical aspects or simulation aspects of what we've developed. These are some of the parameters that we've input into the code. The most important ones, or the most interesting ones perhaps, are the dt that we've run the simulation at, so 1.5 times 10 to the minus 8 seconds. We simulated about 1 millisecond of plasma evolution, and the number of time steps that the number of additional time steps in the electron fluid module were 150. So the dt, effective dt for the electron fluid module is this number divided by this number. And so running these, let's say these simulations in a server at 20 cores and 1.2 gigahertz, or simulations take about 2 days. Okay, so let's talk about the base simulation. I'm only going to show 3 simulations today. We've actually run about 11, or actually more than that, but we only show 11 in the thesis. So one very important thing to note is the alpha anomalous parameter. Again, this is the factor that multiplies the gyro frequency for the anomalous frequency parameter. This is the shape that it has. It's a 2-step or 2 region parameter. It's 0 within the channel thruster. By the way, everything that's negative is within the thruster channel. Everything that's positive is downstream from the thruster channel. And this is the effect over the effective total Hall parameter. As you can see here, the anomalous frequency dominates in the plume, and the result is that the effective Hall parameter is very small in the downstream from the channel, which means that the magnetic confinement is very small there. So let's just show what a simulation of the ones that we've produced looks like. This is a transient response. It's a video of the transient response of the plasma. You can see here the electron temperature, the electric potential, and on the left the plasma density and the neutral density. For those of you that are not familiar with Hall thrusters have what's called a breathing mode. They operate on a non-transient, a transient response, a non-stationary response that is related to this breathing mode here. And this is actually due to a sort of predator-prey mechanism between the plasma density and the neutral density, which you can kind of see on the plasma density here as it goes up and down. So this is what you just saw, the breathing mode oscillations. These are the oscillations in the thruster. We've run an FFT analysis on them, obviously, and it shows that there's a main breathing mode about 20 kilohertz, which is actually spot on with what's been reported in the literature. There's some secondary modes at different frequencies. There's a number of reasons why these secondary modes may be present. They can either be to double ions or some spatial variations, although those are small. It could also be because apparently the breathing mode is a type of senoidal type wave, which actually presents naturally these secondary modes. And we also see these small modes here, which are related to ion transit, and they show a large dispersion between 100 kilohertz and 1 megahertz. The reason behind that is that you can imagine that the particles or the ions that are exiting the simulation domain have a very different history among them. They also have very different masses and so on, so they're accelerated differently within the simulation domain, also because they can become ionized at any point. So this is the dispersion that's associated to using a particle and cell mode or particle and cell approach for the ions. In terms of plasma profiles, I'm showing here the time averaged plasma profiles, so temperature, electric potential, plasma density, and then neutral density, and then the partial densities of single ions and double ions. These are not very interesting in themselves. You can simply see here the single cathode element that we're using. But perhaps more interestingly than those are the thruster centerline profiles, which we can compare with actually experimental results, in this case of Kim, the ones that were reported by Kim in 2002. And just to show you, we've kind of turned around the axis. That's just to be coherent with the axis that he's using. And we can see that the electric potential and electron temperature are actually pretty much spot on with the blue line here, which is the one that represents a mass flow condition that is similar to the one that we're using. The one that's slightly different, though, is the ion current, although we've talked about this within the group, and we're not sure exactly why they show such a steep drop of the ion current as soon as it exits the thruster channel. So we actually believe that our simulation results are more coherent with what you would expect physically. So we can also derive the plasma currents. I'm just going to show a few here. So this is the ion currents. These are the electron currents. These are the total currents, which, as you see, are mostly zero in the plume, but are non-zero between the cathode and the anode, as expected. Excuse me. And this is just a plot of the azimuttal electron currents. And you can see here that the large effect that the beta parameter has over the azimuttal electron currents. They're almost zero here in the plume, and they're very sharp. They very sharply rise within the channel, and that's due to this sharp right of the beta parameter here. I also wanted to point out that the scale of the azimuttal currents and the, let's say, CR currents is very different, and this is related to the fact that the dominant currents in the Hall thruster are, as we mentioned before, the Hall current, which is an azimuthal current. And this is an effect over the ohmic heating. Remember, ohmic heating is proportional to resistivity times the module of the electron current squared. So this is the term that's going to have a larger effect over that term over there. In terms of thruster performances, we're also pretty close, between 5 and 10% different to performances that have been reported experimentally, so we're pretty happy with that. These are some of the some of the current intensities that are obtained from the thruster. I think the main two that are interesting to explore these two. This is the discharge current, and this is the ion current that's being produced, and they're very different. The reason why they're so different is because there's this anomalous transport in the thruster. And in terms of energy balances, we're actually very good, between 1 and 2% error on the energy balances. So we're pretty happy with that. Now, in comparison to a simulation that actually shows an alpha anomalous parameter, we wanted to show the transient response of a simulation that does not have anomalous turbulence, and it's very different. You can see here that you can now actually see the breathing mode also in the electron temperature, and you see this accumulation of density, this kind of half crescent shape here, right outside of the thruster channel. I'll come in a moment into why this happens. But also, not only the simulation is, let's say, not physically similar to the results that we expect. In terms of performances, it's also very different. It's about 30% off with reported performances. So we're definitely in a non-realistic case. But one thing that kind of does give us confidence that we're doing things right is that now the ion and discharge currents are much more similar. And this is something that you would expect if you did not have any sort of, if you only had, let's say, classical transport in the electrons. Just to go over some of the analysis, I'm just showing the temperature here and the azimuthal current, and the red line shows the base simulation, and the blue line shows the simulation that I've just shown you, the one that does not have anomalous transport. So the first thing to note is that the beta parameter, so the Hall parameter, is very different between these two simulations. See here that outside of the channel in the base simulation it drops, where it remains with a high value for the simulation that I've just shown you. This is an effect over the azimuthal electron current, which now has a value that is widely different from this very low value that we saw before. Now, because this parameter is responsible for a large part of the ohmic heating, we're going to have a high electron temperature in the plume downstream from the thruster exit. Sorry. And again, this is a simulation that is not realistic from the point of view of experiments, but I'm just showing the comparison to see what having this alpha anomalous parameter implies. Now, to continue with this explanation, if you look at the electric potential, it turns out that because there's very little conductivity, because the electrons are very confined in the downstream plume, in the plume downstream from the thruster, you have an increase of electric potential, which supposes an electric potential barrier for the ions, and that's because the electrons simply cannot follow the ions if they don't have this added conductivity that we put in here. And this is the electric barrier that is established because of that. And we can see this in the ion currents as well. They drop very sharply here. Now, because of both the temperature increase in the plume and this barrier potential, this is the effects that are causing this increase in the plasma density, this half crescent shape that I showed before. Because we have these three things, we have a reduced neutral density because there's still quite some amount of ionization happening in this downstream region, which is not what we would expect experimentally. Furthermore, since the region between the, let's say, the cathode, which is kind of here, and the thruster exit is very different in terms of conductivity, we see that the axial electron currents are also very different, especially here. That leads, since the, let's say, axial or perpendicular electron current is higher within the channel in the base simulation, this leads to an increased Hall current over there, which is also responsible for the increased temperature within the channel that we see in the base simulation in comparison to the simulation with no anomalous transport. And sorry for looking like this guy when explaining this. I think this just comes to show that the, let's say, the response, the physical response of the plasma, even though we're simulating only relatively simple mechanisms, is actually very complex. As a last simulation, I wanted to show one of the objectives of the thesis was to be able to simulate complex magnetic topologies. So what we've done is we've added a trim magnet to the SPT100 magnetic design. This produces what we call a singular point, a region of zero magnetic field intensity, which you can almost see here in the thruster center line. And it has an effect over the mesh that we're using to simulate, which you can kind of see here, this point over here, that's the singular point. So we wanted to make sure that we were able to simulate conditions like this. We have actually, and the main changes are related to the breathing mode oscillations. They now present a main breathing mode, which is a little bit higher in terms of frequency. They still present the secondary modes and also the ion transit mode. I don't want to go very deeply into why this happens, but it's probably a reason, or it's probably related to the fact that we have a much lower magnetic confinement in the near anode region. And in terms of plasma currents, you can kind of see on the, let's say, on that near anode region that you can see the effects of having this singular point here. You can see that the electron current is kind of, let's say, there's something similar to a nozzle type situation there because of the way that the magnetic field lines are parallel to the wall in the vicinity of the singular point. So this gives us hope that we're actually going to be able to simulate other types of thrusters too. So in terms of lessons learned, well, it turns out that the Hall parameter is very important. The effective Hall parameter is what dominates the plasma response. And the quantitative response can only be obtained as an inverse problem. It's very difficult to know what the thruster is going to do without actually performing a simulation. The frequencies themselves, the physical frequencies, collisional frequencies that we simulate in the plasma are actually vary only very slightly between simulations. But the alpha anomalous parameter is the one that is key here. That allows us to, let's say, do a sort of mechanistic approach towards the alpha anomalous. We can basically consider different zones, and again, this is something that has been done already in the literature. We can consider different zones within the simulation that are related to an asymmetric transfer of momentum between the azimuthal and perpendicular direction, and also the effect that that has over the ohmic heating term. And we can kind of prime or play a little bit around between the region, or play a little bit around with the region between the cathode, volumetric cathode, and the thruster exit to adjust what happens within the channel, which is actually something very interesting because the physics of the channel are the most important in terms of the plasma production. So in terms of the problem, of course, with all of this is that we need experimental knowledge in order to be able to, let's say, adjust this alpha anomalous or to curate the simulation. So computer-aided design, which is something that we were looking after, is sadly not yet possible since we do not have a self-consistent simulation. And one of the things that's interesting is that we've been able to obtain a non-realistic response, but that we believe that is actually due to the model that we've implemented, and it is coherent with the model that we've implemented for the classical transport-only solution. So after all of this, I'll just go over some conclusions. So yes, we've developed a new simulation platform called heightened, which we believe will be expandable to various plasma regimes and EP thrusters. It's about 52,000 lines of code in terms of the core segment, and about 100,000 lines of code for the post and set units. Simulations take about 1 day on a 20 CPU server, and we've tested it on representative Hall thruster conditions. My main contribution, or our main contribution, has been the NOMADS module, which is what we call the nickname that we have for the fluid module, sorry. It's a 2D axisymmetric, 2-temperature fluid module for the electron population, and we've used a bi-Maxwellian closure for it. We also developed a 1D fluid sheath model, which is detailed in the thesis, although we haven't talked about it much today. It's based on a first principles approach and some of the lessons learned by the group. It was expanded to include anisotropicity in the temperatures and magnetic angles different than 0. And we believe that this boundary condition, or having used this model as a boundary condition, allows us to introduce a reactive anode condition, which gives a self-consistent solution of the near anode region, which is actually something also that's new in comparison to legacy codes. And we believe that this unlocks the potential to reproduce different types of Hall thrusters, in particular the TAL, or thruster with anode layer thrusters. We explored various collisional models and data for both xenon and argon propellants. And we've carried out a multitude of simulations and a brief parametric investigation within the time that we've had to assess the interaction of the code segments, the performance, and also the effects of the different parameters in the code. In terms of future work, there's actually quite a lot to be done here. There's some mesh-related improvements that we want to introduce. We want to do element refinement or clustering to better control the quality of the mesh. We want to look into hybrid gradient reconstruction methods and also do a thorough parametric investigation on the weighted least squares method. And we already know, thanks to my colleague Jiewei Tho, that using cylindrical coordinates instead of magnetic coordinates to do the gradient reconstruction provides much better results. We also want to implement new boundary conditions, in particular floating, conducting, and active electrode walls, and also play around a little bit more with the sheath model and some of the models that we've used that go into that model. There's some collisional model improvements. We believe that it would be necessary to, or should be necessary to simulate the excitation, the excited state to first ionization condition by tracking excited neutrals, because it's at least as representative as double ions. We want to explore additional data models, data and models, not only for xenon and argon, but for other propellants such as iodine. We need to play around more with the volumetric cathode model. We want to do some sensitivity studies, and we should look into what happens when you or select volumetric cathode in regions of low density. We believe that the issues that we've seen here can be solved through the inclusion of neutral or plasma flow. And we also want to carry out concurrent mesh refinement and simulation analysis, which means that we will refine both the particle and cell and fluid meshes to see what changes that has. And finally, even though we've developed a model that is based around 2 temperatures, we have only been able to test it in a single temperature or isotropic condition due to lack of time, so this is something that we need to do in the future. There's some very interesting things happening at the moment in terms of Hall thrusters. So there's a proposal to, let's say, work in terms of doing physics benchmarks for these types of thrusters, which has been proposed so that different groups can actually use benchmarks to compare their codes to. So that's something that we'll probably explore in the future. We also want to play around with new magnetic topologies and derivatives Hall thrusters. So, for example, the magnetically shielded Hall thruster that I mentioned before, or a hemmed, or thrusters with anode layer, which, as I mentioned before, could be simulated due to the self-consistent treatment of the anode region. And finally, the search for the alpha anomalous parameter will continue probably for a long time still. Just to finish the presentation, I just wanted to give some acknowledgements and talk a little bit about other things that we've done throughout the thesis. So first of all, to acknowledge the European programs that have allowed me to conduct my research, in particular the KEOPS program for Hall thrusters, and also the Spanish government for their support in carrying out this PhD. I was very lucky to do 2 placements throughout my thesis. One was in the Jet Propulsion Laboratory in California, in NASA, which was incredible. And the other one was at Astra Rocket Company in Costa Rica, and that was thanks to the Santander Bank. And finally, we've done some publications. 3 different publications are the ones that we've, journal publications are the ones that we've worked on, and a few, let's say, conference publications that we've also worked on. Perhaps the most interesting one was the last one, which was the one that won the Young Visionary Award at the last IIPC, thanks to the other members of my team as well. And that's all for me. If you have any questions, I'll take them gladly. Thank you.
Okay, thank you very much for your presentation. Now we are going to start to asking questions to you.
Okay.
So the first one is Dr. Merino, whenever you like.
Okay, thank you very much. Well, first of all, congratulations for your work. I know how much work has been involved in the production of this thesis. I know how hard you have worked for it, so
thank you.
Congratulations for all the nice results, and also to your advisors, Eduardo and Pablo here. I wanted to start with a few questions. I think I have too many, so I will probably just select a few of them, and then maybe if you want, we can
we can discuss later.
Outside, I can let you know some more thoughts. So, well, first of all, I was reading the first part of the thesis regarding the model, and I saw that you take a different time step for the electron fluid than for the peak part. And I was wondering exactly why you do that.
Okay. So as I mentioned before, well, thank you for your question, first of all. As I mentioned during the introduction, once you switch to a fluid model, the, let's say, timescales are associated more to the stability of the equations that you're trying to solve than to anything else. Now, assessing stability in a non-structured mesh is actually very difficult. People don't really do it. They do it afterwards. Actually, they try to basically the way that people do it is they look at the elements in the mesh, and they look at the simulation, and if the temperature or any of the quantities that you're integrating is within bounds, so it's bounded by a lower and an upper limit throughout the whole simulation, then you're in a stable condition. Okay,
you can use a CFL for the
worst
element.
You can do a CFL, but for non-structured meshes, we have a CFL-like condition that we do check, but you can actually not truly assess the stability until you've actually run the simulation.
Okay.
Okay. Now, concerning your question, the number of time steps that was picked for the electron fluid is a response to the stability of the equations that we're solving, and I cannot give you the reason. Let's say I cannot say, okay, we pick 150 time steps within the electron fluid side, because that ensures the stability throughout the simulation. What I can tell you is that we do check an initial CFL condition, and that let's say provides us with this number of steps that you need to run for the electron fluid. Okay. But you can only check the absolute convergence or the absolute stability afterwards, let's say. But it's related to stability.
It's the convective term in the energy equation.
Yes, and it's also the reason why we need to use a semi-implicit approach.
Yes.
Semi-implicit meaning that the terms that are related to temperature gradients, so spatial gradients of temperature within the in the equation, which are related to the heat flow terms, need to be modeled implicitly, because otherwise, if you model them explicitly, you run into a lot of numerical issues. And this is something that was actually already mentioned by other groups. Actually, for example, the JPL group proposed this semi-implicit approach as well.
So if you use an implicit, semi-implicit method, it's unconditionally stable, but probably you don't conserve energy, or is there?
Well, we do conserve energy. That's also where we look at the energy balances. So as I said before, we're less than 1% error on the energy balances and about 2% error on total energy balances between the particle and the fluid module. So we're very happy with that. Obviously, there's going to be some energy that is perhaps lost due to the interpolation of quantities between both sides. So let's say a full balance is difficult to achieve, I think. But I think numerically we're happy with that.
Okay. Thank you. Okay, another question. So you do some analysis. Actually, your first publication is devoted to that, on the numerical diffusion on your grid.
Sure.
Okay. But that analysis is done for a structure grid.
Sure.
If I'm not
structured versus unstructured.
Right.
The paper itself compares a magnetic field that is curved, as magnetic fields are, and what happens when you use a structured mesh versus a non-structured mesh.
Okay. My question was, to what extent you can extrapolate results from a structured analysis, which is not really the case, you have more than that, to a non-structured grid. Okay. And then related question to that one, you have a quite complex mesh, which is the magnetic one. We are aware of the advantages of that one, but given the complexity of generating it and the problems that it brings with, like that somewhere you will have cells that are too narrow because the lines just go there together. I was wondering if there is a possibility of improvement by using a completely non-structured mesh but then you would probably run into other problems. So maybe you can elaborate on that.
So the issue of numerical diffusion has actually been studied in plasmas by many other people. So trying to answer your question, for example, there's different approaches you can follow. For example, you could use a structured mesh that is very refined, which would be equivalent to kind of having a step boundary alongside the magnetic, kind of representing those magnetic field lines. The issue is that, okay, so, and this is kind of tangentially answering your question. The issue is that when you increase the number of elements in the electron fluid mesh, the simulations become also very heavy. As you, let's say, double, for example, the number of elements, that means that you have to invert an equation which is squared that, let's say, that double, so it has 4 times more elements, and inverting that system of equations, or that matrix that comes from the system of equations, for each time step becomes very heavy in terms of computational cost.
Sorry, I understood that you were using the iterative. No, it's the directly. It's a direct solver. It's not.
It's a direct solver. Yes, it's a direct solver. So yes, some people do this by reducing the mesh to a very fine mesh, and that solves the problem somewhat. But this is something that we kind of, I guess didn't predict. But what we saw afterwards is that our code actually, and I'm assuming that this happens for every code that operates similarly to us, as you increase the number of elements in the fluid mesh, you will get a very heavy computational cost. Now, going back to your first question, which was about how do we, let's say, compare structured and non-structured meshes. In the paper that we published, we looked at the transport physics, so cross-field transport physics. And what you saw is that if you used, imagine you had a region that has, let's say, a certain amount of density initially, and then a region that does not have any density initially, okay? And we put those two things, let's say we evolved in time those two things. And what happened was that the diffusion, the cross-field diffusion that you got with a structured mesh, even if you refined the mesh greatly, was still very big. You got a cross-field diffusion that was very big in comparison to the non-structured mesh, to the one that was aligned with the magnetic field. Now, it's difficult, let's say, because obviously having this mesh will give you some issues. So using it as a benchmark, let's say, to compare the structured and non-structured, using the non-structured results as a benchmark is a little bit tricky there, because you're using your own results as a benchmark, so that's not good. But what we did see is that let's say the plasma fills the region that is void initially much faster than if you have a magnetic field aligned mesh. Okay. And that is. The thing is that this also depends on how much confinement you have. And there are regions in our plasma in which the electrons are not so heavily confined. There are other regions in which they are heavily confined. The problem is that you, a priori, you don't know how confined your plasma is. So I think the best course to follow here is to assume that you have a very confined plasma, and you have a mesh that will not show these very increased diffusion in the simulations. Perhaps if we had used a structured mesh, we wouldn't have had to use the alpha anomalous parameter, because we would have had that increase in the cross-field transport.
You already had the numerical.
So we have the numerical diffusion to help us out there.
Okay. Okay, quite quickly, you mentioned the gradient reconstruction,
sure.
Right? And in some of the plots, you have a relative error which is 10 to the 2.
Yes.
Which is quite large.
Yes.
So
so there's a couple of things there. First of all, as I mentioned before, the cylindrical coordinates actually give us much better gradient reconstruction. That's something that we're implementing now. Now, this is relative error. The best way to look at it is actually not with the relative error of deriving an analytical equation and then comparing that with your numerical derivatives, but actually to look at the integration of those derivatives back into the original state, because that's actually what you're doing in the code. So when you look at instead of the relative errors of derivatives, you look at the relative errors of of those integrated quantities, those errors are actually much smaller. So the plots that we show there are a little bit off in the sense that they give an idea that we're really bad off. But actually, what's happening in those regions where you have relative errors that are 10 to the 2 is because the absolute derivative, so the analytical derivative is normally sometimes close to 0, which means that the relative error that you can produce is very high. But if you look at the errors that you commit by reintegrating those derived quantities, then those errors are actually very manageable, to 10 to the minus 2 or lower than that. It also depends on the function, obviously, that you're derivating. So a sinusoidal function like the one that we showed has some aliasing problems in which you cannot really recover what the function is doing with a particular mesh, or also perhaps due to the order of the Taylor expansion that we're using. Our code allows you to use a first order Taylor expansion or a second order Taylor expansion. So perhaps some of the second order terms are also related to the errors that we see there. But we've worked more on that since, let's say, since the initial results, and I think we're at a moment where we're actually quite happy with those.
Okay, thank you. All right. I saw in some of the results that you have in the last chapters that the potential outside grows, so it goes down and then it starts to grow again.
Yeah, I don't know, let's see, well, if you remember the slide, or perhaps...
I don't remember the slide, I have the number of the page. It's 152 if you want.
150, let me just go back to the slide, sorry. Yeah, I think that's the solution for is that the solution for the simulation without anomalous turbulence, perhaps?
I think so.
Yeah, that's kind of what I was trying to mention before. So it's a problem of the
no, it's not that one.
Okay.
This is with alpha whatever, but it's not 0. This one, for example. And I see so you see it in other graphs.
Yeah.
If you compare it with Halma was decreasing monotonously. No?
Actually, those results are from Halma. The blue ones there, or the red ones.
The blue one is the nomads. So it
yes,
goes down and then goes up.
In nomads, you mean? Okay. Yeah. That actually. Let's see. That can be again. We used an alpha parameter for those simulations that was actually, I think, 10%. So what happens is that if your alpha parameter is too small, you still have this confinement effect.
You're approaching that, no?
Yeah, so what happens is that, as you see here, okay, this region here, exactly. So what happens is that what you see here, this increase in the electric potential is due to this confinement barrier that we have for the electrons. The other issue is that those simulations, so this is something that our code does a little bit better, is that as you see there, the mesh that we're using is much closer to the channel than the meshes that we're using now. As you know, the boundary conditions will have an effect on the solution that you recover. Yes. So we also believe that that was an issue related to the boundary condition, the volumetric cathode condition, actually, which is not a boundary condition, being very close to the channel, actually.
So it's an artifact of the boundary and not having enough alpha.
Exactly,
okay.
Yes.
It's not physical. You don't see that in thrusters.
No, you wouldn't see that in thruster. I think it goes down quite nicely, actually, in the experiments. So something more like this. Although you can also see here, by the way, that there is a slight increase in the potential, very, very small, right after the cathode, and it's very flat, it's pretty flat. But actually, for example, JPL in their codes use 100% of alpha anomalous parameter. We use 20% here. So that also is related to the model that you're using for the electron neutral collisionality. So there's a little bit of play between those two things there, which I think is something that I've commented heavily on the thesis. But you can still see that slight increase. And again, that's also because the condition of the volumetric cathode is to have 0 electric potential that you fix at a certain point. So
I see. Okay. All right. One last question. I think this is coming back to something that you mentioned, because there is a lot of uncertainty on the alpha, no?
Yes.
On this anomalous parameter. But given the fact that we depend so much on it and it has such a big influence on the simulations, how much can we trust a code until we have right model for the...
That's a good question, and I think
What is
there's
your opinion?
many various ways of approaching that. For example, in SPC, I believe they presented an approach which was to use machine learning to, let's say, optimize the alpha anomalous parameter in relation to, in order to compare experimental and numerical results. These simulations, okay, so the first thing to say would be that these simulations, these plots of let's say, of the all the plasma quantities are very nice, but also these simulations give you other quantities that that are very interesting. For example, they give you the rate of erosion of the wall, which is something that people are very interested in because we can calculate the sputtering of the ion bombardment in the walls.
That does not depend on alpha.
That depends on alpha. It depends on alpha, but it probably does not depend that much as long as what you're doing within the channel is relatively similar to what happens in reality. Now, the bigger question, I guess, would be what happens when you change the magnetic field topology? Because at the moment, we've simulated a magnetic field topology which at the exit of the thruster is pretty radial still. But people are now looking into magnetic field topologies that are almost parallel to the walls. And I think there's some sensitivity analysis that we should do there to see what the effect of the alpha anomalous parameter will be on that. I can tell you for sure that in the region related to where you're generating your plasma, so within the channel, in this region that you have this high temperature, so if you see, for example, in the response here, so this region over here, that region is and what happens within the channel is very important to the response of the thruster. So that is something that you really need to be careful with. Thankfully, we have these performance results and these, let's say, experimental comparisons that we can kind of look at. But you're right, and I do mention it at the end of the presentation. We don't have a self-consistent model. Yes. I think there's quite a lot of effects that are being looked into at the moment, and perhaps extending the dimensionality of the model would also help to perhaps to see these azimuthal variations of electric electric potential and pressure gradients that give you some transport. So I don't know. I guess we'll have to see. You're right. The validity of the simulations can be questioned.
Well, it's definitely the holy grail of the theoretician right now.
It is. It is. Yes, it's probably, and it's complicated. I mean, you see it in full particle and cell codes. So the full PIC codes derive some quantities for this additional cross-field transport. From what I know, perhaps the modes that are expected to appear don't always appear in those simulations. So you have waves, but maybe not exactly like the ones that you're recovering experimentally. So there's also some differences in that way. So even the codes that are attempting probably to look at that particular problem face some issues. And again, those codes, which are, as you know, full particle codes, take months to run and have other issues. So so it's complicated.
Okay. Well, thank you very much, and congratulations again for the work.
Elias.
Yes, Daniel, well, thank you for your, first I would like to congratulate you for your very clear presentation.
Thank you.
And your thesis manuscript, which is really nice to read, and I've seen a lot of paper clips there. And really, I don't know, like Mario, how much work you put into that, but I can guess that it has been a lot of work and passion in that. So
thank you.
Really, I would like to congratulate you for that. A side remark, just because we don't only congratulate, we can give some advice and pointers.
Sure.
I was surprised to see there's just one paper is really related to the work done there.
That's true.
I think. I don't doubt there is room for one or two more papers on that, and that would be really beneficial for the community, especially some of the work that you've done on your shears model.
Yeah, I believe that when we run simulations that are, and sorry to cut you off, that are two temperature based simulations on the Hall thruster, which as soon as we solve some of the issues that we're still seeing, I think would be the next step. I think those will be definitely interesting to give to the community.
So we can scratch off another question.
But I'll take your note. We're working on it.
And so I'm really impressed by the two main contributions are obviously the 2D anisotropic model, electron fluid model that you developed, and also the sheath model, which is in itself really interesting by its generality. So as I would like just to put a cautionary remark that I'm not specialized in Hall effects thruster, so I would give some questions that I had reading your manuscript and listening to you. I've listed a bunch of questions. I won't go through all of them because we won't have time. But the first one would be like to start with like an easy one, but more like a discussion is about the CPU cost, the cost of your computation. So you mentioned it's something like 2 days per simulation.
Per simulation, yes.
You mentioned that refining the mesh is costly, and so the obvious question there is how could you improve on that by going to parallel computation?
So thank you for your question. We do use parallel computation. We use a single server parallel computation, so OpenMP.
Like an OpenMP, multi-threaded.
We use multi-threaded. We have not gone to MPI, to multiple CPU simulation. The reason behind why we didn't take that step, I think, was initially from the perspective of coding. As you probably know, coding in Fortran can be sometimes a little bit complicated. It has its own complexity, and we're aware that opening up your code to MPI requires you to very, very carefully look at what you're doing in terms of how you share the memory between the different cores, how many let's say calculations you can do per core, and what are going to be the bottlenecks between passing memory between the different codes. So we chose a single machine parallelization in principle because we also had some experience with other codes which weren't parallelized and were also taking a few days to run. So for example, Halma, HP Hall 2 also took a few days to run, and that was our objective, to produce a code that would be in the same range. What we've been able to do through parallelization, first of all, is to go to this full 2D electron model that I've mentioned, which is my main contribution. Previously, we had a 1D model that was also quite limited in terms of the simulation domain that you could simulate. The other thing is that we've been able to increase or have better statistics on the particle side because we use more particles and we use let's say a more refined particle and cell or mesh, sorry, that allows us to recover better statistics in terms of the particles. And that's work that's been done by my colleague Adrian. But I believe we've considerably increased the or reduced, sorry, the numerical noise coming from the particle and cell side. So for what we wanted, I guess we're happy with the way that we've parallelized the code. We're answering maybe more precisely your question related to the issue of the mesh being refined. Let me see if I have. So if you remember one of the meshes that I showed, the issue here is what I mentioned in terms of the fact that lines vary in the relative distance that they show between as you go in the simulation domain. Yeah. So, for example, this mesh is actually a really good mesh, except for the fact that all of these elements here are very, very small and have huge aspect ratios. If we could cluster these elements, which is actually something that the fact that we're using a non-structured mesh allows us to do, then we can use these sort of mesh, which actually has a pretty nice distribution of elements, but instead of having, I think this mesh had something like 2,000 elements, we can probably reduce it to something closer to what we want. And again, same thing here with these red lines over here. So being able to cluster elements or divide elements as well. So for those elements that perhaps are big like this one, or elements that have a large skewness like the ones that appear here, that is something that we can do as an evolution of the mesh. So I think that's something that actually would be very interesting to working as a future introduction into or improvement in the code. So hopefully that will also allow us to keep the number of elements, let's say, to about 1,000, which we believe that in terms of computational load is acceptable in terms of times. That's what gives us these 1 or 2 days of simulations, while being able to retain meshes that are actually good from the perspective of mesh quality.
Okay, thanks. Another question that I have, okay, so maybe this one is, so I'm not familiar with the art of choosing the anomalous.
It is an art.
Anomalous coefficient. So obviously, what strike me is the fact that you cut off the coefficient inside the channel,
sure.
or closely to the
yes.
channel. So could you comment on why it is
okay.
chosen like
so
that?
There's been a lot of work in terms of why this anomalous collisionality occurs, and there's been I'm not the first one by a long shot to propose a 2 or even 3 region model for the alpha anomalous parameter. Again, maybe going back to what I mentioned at the end, it's a bit of a and I'm just going to take this off because I'll just talk like this because my ear is killing me. So if you look at it from the mechanistic point of view, if you increase the alpha anomalous parameter within the channel, that has a direct effect over the azimudal Hall current. As I mentioned at the end, the transfer between momentum between perpendicular and azimudal directions is not symmetric. So in order to increase a little bit the perpendicular transfer, you end up losing a lot of azimudal current. That has an effect on the temperature that you can reach due to the resistive heating. And you see from the simulations that if you put a little bit of alpha anomalous parameter within the channel, then your temperature goes down. And I did have other results, and you've seen them in the thesis, where I'm using a 1% alpha anomalous parameter within the channel. And that produces a temperature which is closer to 10 electron volts, or closer to 10 electron volts, while the experimentally reported temperatures in the SPT 100 are about 20 or more electron volts. So the mechanistic answer to that would be just by looking at the simulations. Once you look at the let's say average temperature there, you notice that that's not realistic. Okay, so that's the way I would look at it in terms of if a future user has to check this out, they should look for these sort of clues. Now, in terms of the physics, there's various answers to that. So, for example, one of the assumptions of what's causing anomalous turbulence is the ion acoustic mode, which is due to the fact that can be due to the fact that electrons have a much larger azimudal current than ions. And for example, JPL has proposed that this happens because of the cathode. So the cathode is introducing this mode into the plasma, and it is the one responsible for this ion acoustic mode, which produces these wave-like effects in the plasma that are then responsible for an increased cross-field transport. There's other people that, so for example, initially some people assumed that either electron scattering due to secondary electrons that are coming from dielectric walls, or because of the micro roughness of these walls, was causing a short circuiting of the electron transport near to the walls, which is this near wall conductivity that we spoke of, which, by the way, we do not model in our simulations, because we believe that, or at least from the perspective of making them more simple, having one parameter is better than having two and having to adjust them. But again, there's a wide variety of reasons why this could happen, and it's not very clear, I believe, from my knowledge on the current state of the literature and the community, why this is actually happening. There's a few guesses. Jean-Pierre Booth gave a really good presentation on this on last year's IAPC, and he mentioned that it could be, for example, the E cross B drift that's happening because of wave-like gradients in electric potential in the azimuthal direction could perhaps be solely responsible for this. We don't know exactly, because the simulations that we've run in the r theta or zeta theta dimensions are not conclusive in that front, although they do show that there's this wave-like effect that is producing cross-field transport. So it's probably, and this is kind of quoting Ben Jorns, it's probably a sum of effects, to be honest. And I guess the question now is, are we able to discern which effects are primary effects and which effects are secondary effects? But it's again, it's difficult to answer why we choose a particular alpha anomalous parameter. The only thing I can tell you is that from a mechanistic point of view, it's very clear what you need to do with that parameter, and that if you add alpha anomalies within the channel, the temperature is going to go down. It's not going to look, it's not going to give you the temperature peak that you expect from experiments. And if you don't put alpha anomalous parameter in the plume, as we've seen, you get these weird potential barriers that do not make sense experimentally either. So, so again, my answer in that front would be more of a mechanistic answer.
Okay, thank you. Well, a remark, or I was somewhat surprised, and I guess that you will see that question coming. I was a little bit surprised by the model that you should choose for the elastic collisions, for electron-neutral collisions.
Okay.
A constant,
Yes.
choosing a constant
Yep.
cross-section,
Yep.
which is quite off from what you would expect from a realistic measured.
Yep.
And so you commented on that, and I'm wondering why did you keep this? Did you keep it, or is it something that is a parameter and you choose it for the presentation of your work? And
so that's actually kind of like a legacy thing. We've and this is just a slide I have prepared to talk about collisional models, but I didn't put it in because I was way over time, which I've probably been. But we did explore various collisional rates due to different models, and we were very, very interested in the electron-neutral collisionality because it's the main collisionality aside from the alpha anomalous parameter. Now, we explored this Michener-Kruger model, which is the one that you're mentioning, for a constant cross-section. We also explored a non-constant cross-section given by Hayashi data, which I think is also something that within the community is very well known, and a model that was used by JPL for HP Hall 2 that I found in some of the literature, which was this model by Makiran and Stauffer. And as you can see here, there's actually quite a lot of variability, especially as you move alongside the electron temperature in terms of the in terms of each of these models. So I believe if I'm correct, so this dotted line here is the Hayashi model, whereas versus the fixed line, which is the one by Michener-Kruger. And this gives you a very different result. This will give you widely different results. Now, that's bad news in terms of let's say, of using the Michener-Kruger model. And in the first iteration of this presentation, I actually also showed the results that came from using the Hayashi model. You have them in the thesis, so we can also discuss them. But as you can see, the fact that you have a reduced collisionality produces smaller temperature profiles. You know, kind of the expected things. Now, one of the good things about having this mechanistic approach towards the alpha anomalous parameter, and this is something I mentioned before, the region between the cathode and the channel exit is very important. And you can prime that region with a higher anomalous turbulence to have an increased, let's say, electron current being extracted from the cathode, which then compensates for the reduced collisionality that comes from using the Hayashi model. So we can still get very similar results, and this is a simulation that I have not shown in the thesis, but you can still get similar results to using the Michener-Kruger, so this constant cross-section model, if you increase the alpha anomalous parameter outside.
I'm just seeing the thing a little bit the other way around.
Okay.
I mean, for the Hayashi model, for me, is the one based on the cross-section that you found for the elastic collision.
Sure.
So this should be the I think I would put that as a baseline.
I
understand for
yes.
legacy reason you have this model, but and then you can play with the parameters to find the peak.
I agree with you. That is something that perhaps would have been.
Maybe you did it already. So
it would have been. It would have definitely been a better baseline. I would say. We were in a weird transition between showing results that were coherent with what we had before, and we saw that this parameter had a big influence, and also showing results that were new. And to be super honest, if you look at most of the literature in Hall thrusters, people still use the Michener-Kruger model.
I didn't know.
They still use that model, and you see that if you use the Hayashi model, you get different results. People even use the McEran-Stoffer model, which actually gives you an added collisionality, so a collisionality much larger than the one predicted by Hayashi experimentally. So this is maybe a little bit of cheating in the sense that you say, okay, we don't know what the alpha anomalous parameter needs to be, but if we have a collisional model that is big enough, then or alpha anomalous parameter can be small, and we don't have to go too much into explaining why we have such a big alpha anomalous parameter. So I think that maybe is a little bit of cheating from the point of view of other results in the literature, but we've also done it, and I agree with you. You're completely right. I think it would have been a better baseline to use the Hayashi data for that.
Right, okay. So one last question, and it's about the difference. I didn't understood in the way you present the difference between the semi-implicit model and the explicit model.
Sure.
So you present your residual, which are, if I understand correctly, not decreasing for the case of the explicit model.
Mm-hmm.
But if I remember, those are for steady-state solution, which are not steady, actually, which are oscillating.
So actually, they're just a steady-state solution from the perspective of the particles. They are. I'm just looking for the slide. Sorry, one second. Okay, here they are.
Because in your simulation, I would expect the temperature and the potential to oscillate a little bit because of this breathing mode. So somewhere the residual shouldn't change because.
So what we're showing here is a single particle time step. So imagine that you have frozen, heavy species. So you have a frozen neutral density, ion currents, everything. Okay. So when you freeze these, you can then allow the electron fluid module to evolve for however time it wants to reach a stationary condition. A question would be, obviously, how big are the residuals when you run a simulation that is oscillated? And I can tell you that we've also have results for that, and they're shown in the thesis. The residuals, the exit residuals for the electron model are 10 to the minus 3, 10 to the minus 4. So I think, again, numerically, we're happy with those. What this is showing is simply the fact that if you use a time step, and again, this is for two simulations in which use the explicit time step, the explicit approach and the semi-implicit approach for the same delta t. Now, when you use the explicit approach, what ends up happening is that you enter this kind of oscillatory mode in the temperature profiles, and the residuals simply never go down down from this. Versus in the semi-implicit model, in which you're modeling implicitly those terms that are related to temporal gradients, which you do see the residuals go down almost arbitrarily. Now, I think that kind of that shows us. We also saw, and I think it's mentioned very briefly in the thesis, that we saw some other issues, numerical issues, with the fact that because we're using an explicit time step, certain let's say the evolution of certain of the temperature profile in certain elements would be from one time step to the next would give you this a very strange spatial solution for the temperature, which was actually the fact that you were not using a DT that was small enough. So it was just completely prohibitive in terms of computational cost to go down the explicit route, and also because of stability reasons. So we also obtained results that were non-physical. So that's why we discarded it almost initially.
Okay, and maybe one last, if you allow me. The comparison that you showed with the experimental performance parameters of the thruster are really, really impressive. I mean, you have really good agreement with the experimental data. Did you look at other kind of experimental comparison? Especially, I'm thinking with your PIC module, you get the ion velocity distribution function, for example. Are there any available data on SPT100 regarding those data?
Yes, I believe there are. There is data related. I think you're mentioning. Let's say where are the performance results. I think they're here. Yes. So there is data related to the ion velocity distribution function. The reason why I haven't shown that data, and even though it's available with the data that we have now, is because we've tried to keep separate, let's say, things that were related to the particle side, which obviously my colleague developed, and things that were related to the electron fluid side. Perhaps I also had a little bit more experience dealing with previous legacy codes from work I did at the beginning of the PhD. So eventually my thesis was also focused on complete simulations. But things like particle statistics, the distribution of the neutrals and the velocity distribution function of the ions, it's something that I believe my colleague Adrian will report sometime in the future, probably in his own thesis. So yes, we do have that, and I would assume they would, I can't really speak for it because I haven't done the comparison, but I would assume that they're fairly comparable to what's being measured out there.
One thing that those data can give you is the acceleration profile and the potential profile inside the channel.
Sure.
Which is something, well, you can say it's a fluid quantity, so maybe I can
okay.
compare it.
Okay. Yeah. We'll have a look at those for sure.
Well, that was maybe we can discuss some more later on. I won't grab hold of the time. So thank you again.
Perfect.
Congratulations for you. Really great job. Thank you.
Thank you.
Thank you. So now it's my turn, and I would like first of all just to congratulate you because of the work you have done. So the extension and the quality, both of them.
Thank you.
So let me ask you a few general questions regarding the modeling that you have developed in your PhD thesis. So the first one is what kind of equation, of field equation are you solving? Are you solving the full Maxwell equations?
No.
Because you mentioned also the okay.
Yes. So no, the Maxwell's equations are not solved. We kind of do a little trick here, which is the fact that we consider the magnetic field to be static, irrotational, and stationary allows us to discard a few of the Maxwell's equations. And at the same time, the typical equation of Maxwell's equations that is resolved, particularly by full pick models, is the Poisson equation. We don't need to solve that because we use a null Debye length assumption. Which allows us to assume that there's quasi-neutrality in all of the let's say in all of the simulation domain, and therefore the electric potential actually comes from a fluid type approach, which is the one that we obtain from the momentum equation. So the generalized Ohm's law is the one that's responsible for giving you the electric potential solution. So no, we're very lucky in the sense that we don't need to solve Maxwell's equations in this case. We also don't have electromagnetic waves in Hall thrusters, although other thrusters do have them.
Displacement current. Okay.
And no displacement current, exactly. So we don't need to solve for those. So within the simulation domain, there's a few assumptions that we can do that allow us to forgo, let's say, the Maxwell's equations, which would be more complicated to solve.
So in that case, I don't see clearly how you make a peak simulation and then you obtain the ion current.
Yes.
And you may image the simulation and the electron current, and they do the fields where do
the electric and magnetic fields.
From?
Okay,
yeah.
so the magnetic field is imposed externally, completely imposed externally.
No self-consistent.
Yes.
Okay.
That's
this
what
okay.
So the other assumption is self-negligible field production. Negligible self-field production. We assume that the production, the magnetic field production of the plasma is very small compared to the applied magnetic field. Okay. So that allows us to also, I was missing that assumption. You're right.
Now it's clear.
Yes, and obviously the electric
something is missing or is
and the electric field comes from deriving the spatial gradients of the electric potential.
I don't see clearly as well regarding the model. How do you make the time integration of the equations?
For the electron side?
For the particle itself, for the MHD, or the fluid equation, and for
so the temporal evolution of the particle and cell side is simply related to let's say the electric field and the magnetic field is computed locally on the particle. And then they simply integrate the temporal evolution of velocity and space through Lorentz equation. So you're only applying Lorentz equation for that. In the integration of the electron fluid, as I mentioned before, our dimensional analysis allows us to assume that convective and non-stationary terms, both in heat flow and momentum equations, are discarded. So only the energy equation has a temporal evolution to it. And we use the finite volume method. We simply integrate the equations spatially. We do the integral over the volume of all of the contributions to the energy equation, and we use and then we use a semi-implicit method for the time step. So we use a forward and backward Euler's method for the temporal integration, and that gives us let's say the rate of change of the pressure term, actually in this case, or the temperature term.
So let me add a comment here. I think that the full implicit simulation should be unconditionally stable. So why do you semi-implicit? I don't know.
So the problem, it's a numerical issue. It's more than it's more of a numerical issue or a complexity issue. Let me just go back to that equation a second. Okay, yeah, I think it's here. So the problem is that if you solve these, if you solve all the terms implicitly, So if you solve all of the terms implicitly, so at the moment the terms that we solve, let me start again. At the moment the terms that we solve implicitly are the ones that show this T1 here, okay? Now the problem is that some of the other terms in the equation depend, for example, on the electron currents. Okay, the electron currents has a term that depends on pressure gradients, which is what you're trying to resolve, which means that you would have to iterate between these two equations in order to obtain, a fully implicit solution. Yeah. Or perhaps there's a way, I haven't played with the equations to that extent, in which you can introduce, let's say, this equation here into this one and resolve the model altogether. I'm not sure that's actually possible because of what the equations are telling you. But the issue here is that there's terms that are related to electron currents and the electric potential that you would imply that you have to iterate between these two equations. And one of the initial, it was an assumption, but it was an initial, let's say, decision that we made was that this was going to be prohibitive computationally. And also it was something that perhaps we could do at a later date. So we went on to do the semi-implicit method. And by the way, the semi-implicit method is implicit for those terms that are explicit with temperature and explicit for those terms that are implicit with temperature. Okay. So that's the approach we followed. But it was more of a computational toll issue.
I have another question which is related with the meshes. Okay. So we are using a distorted meshes for hydro.
Say that again.
A distorted mesh for the hydrodynamics.
For the electron dynamics.
MHD. Yep. And then
a structured mesh.
Eulerian mesh for
the particle.
And
yes.
Then how do you put the
there's an interpolation step,
and it's a very difficult trick.
Yeah, I didn't talk much about this in the. Not even in the thesis really, because it's more of a numerical thing. But if you see here, there's two interpolation steps between the particle quantities and the fluid quantities. So you interpolate between them. Okay. This interpolation module is actually also based on the weighted least squares function or gradient reconstruction that we also use for gradient reconstruction. So it's also based on the same method, and it allows us to interpolate between quantities here to the quantities there, and vice versa. We've also done some analysis on how good the interpolation is. We interpolate forward and backwards, and we compare the relative errors of forward and backward interpolation for the same analytical functions that I showed for the gradient reconstruction, and those errors are actually pretty low in terms of the interpolation of the meshes. So
you preserve the balance, the first order moments.
Or
something else.
Say that again. Sorry.
That you preserve the balance, the first order moments.
Right. So that will have an issue in terms of the energy balances, and obviously let's say, for example, what electric fields the particles are actually seeing versus the electric fields that you recover from the generalized Ohm's law. So those will have small differences. I think those differences are actually accounted for in that percentage of power balances that I spoke of, which are, some of the simulations are not as good as that 1 and 2% that I showed. Some of them go up to 5%, but still we're pretty happy with numerically, I think, with the fact that we have less than 5% error on let's say the energy balance. But by the way, the electrical energy power balance, the one that's only associated to the work of the electrical field, is always very low. It's about 1% or less between the two sides. So I think that proves that we are somewhat conserving the quantities that we're interested in, even considering the interpolation steps that go between the meshes.
And one last question about the balance between the particle in cell and the fluid model.
Yes, I can show the
in terms of the execution time.
In terms of
the execution time.
I'm afraid I don't understand that last bit. What do you mean in terms of execution
Which one
time?
is the most costlier?
Oh, in terms of execution time.
Cost-
Oh, okay.
execution
Sorry.
time.
Yes. I know what you mean now. It's the fluid. It's sadly it's the fluid part. The inversion, which is it's my cross to bear. It's the inversion of the matrix is quite costly.
More than peak?
Yes.
Oh.
Yes, actually, it's more than the pick. We thought it would be comparable, and it used to be less in previous codes, actually. But having gone to a 2D model, and because of all of the conditions that we need to put into the electron equations, actually, that's not even the case. It's really the inversion of the matrix that's giving us the problem. So 1,000 by 1,000 element mesh gives you simulation time where it's probably like 2/3 to 1/3, actually. So that's something that.
And have you ever thought in the possibility of applying particle in cell for electron and ions for both species?
Yeah, but actually that's worse because if you use a full pick approach,
it's more expensive the fluid than pick.
Yeah, but not. But the problem is that modeling the electrons is maybe, I don't know. It's the mass ratio, so you need to take into account the mass ratio, which is what 200,000 or something like that. So
you should not need to resolve the gyro motion.
You should not need to resolve the gyro motion. So
No.
you mean reducing the dimensionality of the problem.
Exactly, and then you can do the electron calculation faster.
There's a lot of kind of
MCF
shortcuts
people do that.
in full particle codes that either reduce the dimensionality or actually alter the base physics, like the permeability and things like that, in order to have better simulation times. But if you look at the literature, the truth is that if you go for a full pick model, these simulations go from 2 days to 2 months, and that's accounting for perhaps not even modeling, the downstream of the thruster, or maybe only a section of the thruster using periodic boundaries and so on. So the reality is that full pick simulations are still much more expensive than the simulations that we run here.
So I think that what you are saying is true if you are looking to run the code in 20 processes or something like that.
Mm-hmm.
If you go to 10,000, okay.
Yes,
there is
you
not
can
any
also
problem.
scale.
You can have the results in 1 or 2 days as well.
Yeah, you can probably you can do a better scaling. That's true. But I think Paul is kind of maybe doesn't agree that much. I think I'm not an expert in full pick simulations, but from what I've seen in presentations and conferences and so on, I believe that presently, even with supercomputers and MPI parallelization, people still take a very long time to obtain results, or they have to reduce the let's say the simulation domain and do some non-physical artifacts in order to reduce the simulation time. So I think it's still complicated.
So perhaps to scale down the model. No?
Yeah,
to
scaling.
Scale down, something like that.
Yeah, scaling. So for example, one of the things is that if you look at a full pick result, and there are plenty of full pick results for Hall effect thrusters, and there are plenty of them. They almost never look into the performance of the thruster. It's always about wave-like effects, or what's transient effects between the electrons and the ions. but they're never able to resolve the timescales that we're looking at. So, for example, I think it would be very difficult to see a full characterization of the breathing mode that we've shown in a full pick approach.
But in any case, I think that to use a full pick code will be a very good tool to compare.
That's true.
For Bergman
yes,
to compare your
I completely agree,
calculations.
and I believe it's something that I think our group will be interested in the near future.
This may help you to fix these parameters,
The alpha anomalies,
or something like that.
Yep,
Otherwise, you know what
that's the idea actually. And
this is because the simulation is not fully self-consistent.
Yeah, I think it's, and you're right about this. It's about perhaps looking at scales and kind of deriving some quantities from certain scales that you then input into the larger scales, and then you can kind of iterate between those two things to actually attain a self-consistent simulation, as you mentioned. So yes, you're right.
You can
about
put more physics into your model.
Yeah.
In that case. Okay.
Yeah.
That's all from my side.
Okay. Well, thank you for your questions.
Any other question?
We'll discuss.
We'll discuss later.
We have dinner later, so there's time to discuss with a little bit of wine, maybe.
Thank you very much for your clear and bright presentation. Okay. So now it's time for discussion between the members of the jury, the tribunal. So, sesión privada.
There is a comment.
There's questions.
Yes.
Doctors.
And also, if there is any doctor in the room, they are allowed to make.
There's one behind you.
Yeah, there is.
Make a comment, just
Okay.
a comment, okay?
Go ahead, please. Go ahead.
Quick comment. Anything to talk about hybrid, etc., and whether we need to integrate the J motion. Okay, I'm not going to comment on that. Perhaps later. But just about the consistency about the Maxwell equations. Okay, we are working on the electrostatic zero beta limit of the plasma. So in that limit we are being consistent. Okay. So and the actual beta of the plasma is quite small. In that sense we are consistent. That is why it's not pure MHD where
Okay.
Okay.
Okay. Thank you.
Okay.
I think
No other comment?
there is no question.